Exciting speakers that I'm going to call to the table. And first one is Dave Nichol, who is with the electrical engineering department here at the University of Illinois. He's the director of the Information Trust Institute and also the director of a couple very large research centers. Second speaker is my colleague Tom Overbye, also here at Illinois. Founder of Power World and very well known in the power community as well. And then the third person is another very well known person in power, Miroslav Begovic from Texas A&M, the department head there. So thank you all. So I guess we're going to get things started with Dave Nichol. So Dave, is all yours.
All right. Well, thank you very much. I was telling Tom, let's see, slideshow. Yeah. How do I open something? I'm sure. I close that. Mine's up. Where are the Wednesday afternoon? Tuesday afternoon. Today's Tuesday, right? My name on it. Okay, very good. So I was telling Tom that I reviewed the email with instructions for this particular presentation, and there were two things on it that stuck out, and one was that I should take about 20 minutes, and the other was that I could talk about anything that I wanted to. And I said, oh, the opportunities. So, you know, I've got a hobby of building hammocks that you use when you camp. So I could give you like 20 minutes on the engineering principles of camp, but I sort of suspect that wouldn't go over so well. So I'm going to take a miss on that one. Unless somebody wants to invite me to give that talk, I'm happy to prepare it and happy to give it. But we'll take a pass on that this time. So then we'll go down to Plan B. Plan B, making sure that what I did talk about had some intersection with what we are all here to think about, is energy. And so I thought that I would brief you on a new activity that we have at University of Illinois that's called CredSEE. And so we are just finishing up the first year of CredSEE. I'll talk more about the participants and so on, but it's a large center that's funded by the Department of Energy with the objective of doing, taking an academic view of issues related to resiliency, cyber resiliency in the energy delivery systems. Oh, I got to tell another story. I can tell a story like 20 minutes, right? So CredSEE, you look at it, and that's kind of an awkward acronym. And so can't you guys come up with a better acronym? And it shows like you're a bunch of engineers. You come up with an acronym like CredSEE. And so when the call for proposals came out and we formed up a team and we rented a conference room at the Admirals Club in O'Hare and had 20 people in a room. And we thought hard for about 45 minutes and different ideas about an acronym for this activity. And we hit upon the perfect one. And it was Resilient Energy Delivery Institute, READY. And say, we are ready. And I could imagine T-shirts and okay. Yeah, we were ready. So then, because we were ready, we were sending out letters of asking our friends in industry if they would like letters of support for this activity. And so they started coming in, and there was someone from Siemens who sent me a link, and he said, "Say, is this the call for proposals that you're responding to?" And my first inclination was say, "Well, of course." But good thing I didn't do that, because what it is I followed the link. And here I found out that the Department of Energy had an open BAA, same time as ours, for the Resilient Energy Delivery Infrastructure. Ready. Oops. So we had to scramble fast to try and remember and resurrect, the Plan A and the Plan B and the Plan C and so on. So that's how we came up with CredSEE. I'm sorry, we tried to do better, but we got what we got. And okay, so what is it in a nutshell? We are working to identify and perform cutting-edge research and development, and I want to emphasize this, and that's why I put it in bold so that you notice, whose results are actually used to increase cyber resiliency of energy delivery systems. So to get there, there are a number of objectives that the Institute needs to achieve. One of those is new for us, but I think really important. If you want something to really be used, you have to convince the guys with the checkbooks who make the decisions to buy it and to use it and to invest in it. And so we have activities to try and understand the view from the C-suite of investment in cyber resiliency. And what that means is this is probably the only place I have in this deck to talk about that. But what that means is looking for technologies, looking to develop technologies that not only protect your cyber infrastructure from the really bad day, when the guys from Ukraine come after you rather than their buddies in Ukraine, but have value every day. And so the investment strategy there is, look, if you invest in this, then you can understand your business processes better. You can make better decisions. And a lot of what the state of the practice and the state of the art is in this space now is in monitoring and gathering lots of data and analyzing it. Yeah, to see if you got some bad guys in your midst or conditions that will let bad guys into your midst. But all that same data allows you to have a better understanding of what's going on in your system. Data you can use to optimize your system. So that's the kind of arguments, those are the kind of thinking that we got to come up with to convince the C-suite that they ought to be investing in this. Other things that we need to do is to identify what the impediments are to cyber resiliency and find the highest impact adoptable solutions. This time I thought I would emphasize with italics rather than bold. Adoptable. It's all fine and good, and it's great. We have lots of people here who do great theory. And when I was young, I did great theory, at least I did theory, and that of things that were of interest and are publishable and are deep, but are very, very far away from what can be adopted. And so we said, hey, look, we have such a large space, such a large platter of problems to work on. How about let's prioritize for this project, let's prioritize on the ones that can actually be adopted, because there are impediments, all kinds of impediments. There are technical impediments, there are economic impediments, there are policy impediments for doing some of the things that you might think of doing. So we're going to take the path towards the things that can be adopted. We need to validate these high-impact solutions with industry. And so we have structured the way that some of the projects are set up so that we have direct industry participation in the prioritization and selection of those projects. And some of these projects, even to have the project, you have to come with an industry partner or be willing to have an industry partner foisted upon you to develop the thing so that at the end of the project, then there's someone there who's ready and willing to help validate it, make sure it's doing the right thing rightly or correctly, and possibly be used in their own context. We need to make those solutions available, different ways of doing that. One of the ways that we have done here at Illinois somewhat successfully is to have startup companies. You might have heard of one or two of them, at least one of them. Other ways of doing that is to work on open source solutions, which does not mean, to have impact does not mean that you have open source. Hey, I got open source, come and get it, there's the GitHub. No, you have to build a community around it that's using it, so that it has a life of its own. It has people that are using it and maintain it and keep it going once it's done. So you need to make solutions available. And we have the extra interesting challenge to make this whole operation self-supporting at the end of 5 years. So we've been supported by DOE for quite a while. And this is sort of like in the BAA, you look at it and say, you've done great for 10 years. This is the last time we're going to support you. After that, you're on your own, Jack. Well, that's sort of a paraphrase. But what it means is that they want us to have a model for having industry, if somebody's supporting this activity once it's done. So that's a real challenge. We are a university. We have educational goals. I didn't capture my watch, so I better speed it up a little bit. The CREDC research team, here we have cast of many, and we are organizing all of that. Some of these partners are ones that we brought with us from past projects. Some of these partners are new to us, but you can see it's quite a diverse group. Here's the elevator picture. Although I guess you don't show elevators, pictures in elevators, but as far as emphasizing the role that industry has in our thinking, is we have sort of strategic things that are happening and tactical things that are happening. At the strategic level, we have an industrial advisory board. They're helping us identify what the long-term needs of the industry are, certain things that you can do with that. And goodly number of our projects fit in the category of long-term research, which means that they are, maybe 3 years out from actually being, at least 3 years out from actually having an implementation. We have midterm research and development projects. Those are the ones that directly involve industry. So they're helping us prioritize the things. So they say, yep, we'd like one of those. If you gave us one of those, by gum, we'd use it. And then also participate in the validation and verification of the stuff as it comes out the other end. So the trends that are shaping this, and believe it or not, I am going to actually get to renewables. I think I might even have a slide someplace that says renewables in it somewhere. So yeah, it's coming up. Technology that creates new attack surfaces. And so there are all sorts of things that are happening. There's Internet of Things, there's cloud, there's distributed generation, there's electric vehicles that are coming down the way. Things that are all possible because you're using CPUs and communications to do things amazingly better and faster and cheaper, but also allowing the bad guys more ways in, or just the complexity of the systems to up and fail. And so those are challenges. The adversary is evolving. Security is sort of like a game of whack-a-mole. You slap them down one place and they figure it out and they pop up another place. Other things that that shape what we do has to do with push towards standardization and compliance. Told you I was going to have renewables in there. Let me stop and pause on that a little bit, because I think that's, you're talking about renewables. So, you have the wind farms and other sorts of ways of having renewables. What you have here are much more challenging control systems, as I'm told by my control peers. Communications. To make this work, you need to have a lot of data, a lot of forecasting, a lot of active control. All these things are places where, if they were wedged somehow, either by a backhoe or by a denial of service attack that kept the control systems from being able to talk to the devices that are doing the control, bad things happen. And so, to the extent that what we're focused on is the resiliency of the cyber infrastructure that helps control these things, then that's the connection to renewable for sure. And that sort of gets also into the increased monitoring and control that we need to have, because the recognition is, and it was a long time to get the Department of Defense to buy into this. Before they bought into it, the idea was, from their point of view, security, build me a honking great wall around this thing so nobody can get in. Well, it hasn't a wall yet been built that does that. They always get in. They have tunnels, they have drones, they'll get over the wall somehow. So what you have to do is you have to expect that it's possible for something to be in your midst. And so that means that you have to architect what you're doing in such a way that you can monitor and see that it's happening, and react to it in a way that is resilient, that keeps you working even when you've got a bad one in your midst. So the ways of doing that is monitoring and control. So research areas, and then I will yield the floor to my esteemed colleague. One of my esteemed, I'm not sure which esteemed colleague I'm yielding the floor to, but I will yield the floor for sure. We have one area in cyber protection technologies, and so the idea here is that we have this cool new energy stuff out there that needs to be protected, and so these are the technologies that we developed to do that. I mentioned before the importance of cyber monitoring, metrics, and evaluation. This gets into the whole issue of gathering lots and lots of data and making sense of it. With the piles of data that you have to turn data into information, and information into knowledge, and knowledge into action. And so that's a challenge in all sorts of ways. And there's lots of aspects to this that need to be considered. Risk assessment, really big. Harkening back to the C-suite, who wants to understand what the risks are, what are the costs. If we invest this way, what's going to happen, what's not going to happen. So this requires sophisticated modeling and analysis and data analysis, so that's a big deal. Data analytics, touched on that. Privacy is actually an interesting problem, and I think I'm close to done. So privacy, in this brave new world where we have of lots and lots of information being shared for all kinds of reasons, you have to be concerned, or if you're someone who owns data And there are incentives for you for sharing data, but there are also disincentives for sharing data, and that is data that's shared might be analyzed in a way that reveals things that you don't want to have revealed. So I won't pull out my privacy deck, but no, it is possible. It's not just to go to a bunch of data that's been collected and take out the person's name and social security number. I mean, there's all kinds of information in these data records that, when you have enough of them, ask the right questions, triangulate with things that are outside of that particular database, you can make inferences about things that are going on in that data, that the data reflects something. And that's loss of privacy. And so when loss of privacy means loss of intellectual property or security, then that's a bad thing. So we have to pay attention to issues there. Architectures and networks, that's a communications and computer thing, and the impact of disruptive EDS technologies like renewables on EDS. So with that, I don't know, do we take questions now, take questions later? Take questions later, all right. So, very good.
Okay, so I'm going to talk about some of the aspects of integrating renewables into the grid on a more shorter time scale, what we power engineers consider the transient stability time frame. This kind of builds on some of the things that Steve talked to us about last night. I'm a power system guy, and I think electricity is a great way to move energy. And we electrical engineers are hoping to take over more sectors of the energy economy. Transportation is the one that we've got our sights on right now. Karuba Haran, who's here, he's right there. He walked over with him. He's working on us taking over a part of transportation I thought we'd never get, which is aviation. So we're going to be flying electric aircraft pretty soon. Most of our non-carbon energy is converted into electricity, and these options really require a grid. Kind of my view is the off-grid options where you have your mountain cabin, you're living on your own with your solar panels, that'll work for some people, but I don't think that's going to work for most people. So I think we're going to have a grid, and we're going to have a grid going forward that's going to include a lot more renewable, and we have to deal with it, and we have to deal with it on a number of different time frames. This is a pie of where we got our energy, and as Steve pointed out, it's fossil fuel. It's 81% fossil fuel now, 86 in 1990 and 2000. Wind is growing. It's 1.9% of our energy now. Solar, with Miroslav's going to talk a lot more about, is growing. It's a small sliver right now, but it is becoming increasingly important. Our renewable consumption is growing, but it's still not that large. The largest chunk of it is hydro, and that's been around forever. We get actually a good chunk of our energy on electric form from biofuels. A lot of that is wood that's burned from the paper industry, but solar and wind are certainly growing. That's a graph that shows how the wind capacity in the US has grown over the last 16 years. Right before this panel session, I was teaching my power system analysis class, which I've done many times. Alejandro's served his time in there too. When I started teaching that in '91, we never talked about wind. I mean, wind had no role in the grid. Now, about 7% of our US capacity is wind, and it's something that we have to deal with. And I'm going to cover some of the more technical aspects of it in just a second. Where is the wind? There's a lot of it here in Illinois, and if you drive around, you see it from the highways and byways. But Texas is #1 of that 70 plus, about 18,000 of that is in Texas, and then California. So it's in many portions of the country, but if you look at that graph, it is not in the southeast. Okay, and they just don't have the wind energy resources that we have in other parts of the country. this is the price of natural gas. And when you talk about integrating renewables into the grid, you have to consider how natural gas prices change, because natural gas can be converted into electricity pretty efficiently. We know the conversion rates. It's about, if you take the price of natural gas in dollars per megabtu, it's about 7 to 10 times that to get the dollars per megawatt hour. So if gas prices are high, renewable generation looks really good. If gas prices are low, renewable generation does not look as cost effective. And right now we're dealing with gas prices that are lower than I ever thought they would be. They're as low as they were in the 1990s. And you know, this affects the grid. Here in Illinois, it affects the economics of power plants like Clinton. And as you know, if you've been following in the news, Clinton might be retiring. For those of you who aren't from Central Illinois, Clinton is our local nuclear power plant. It's about 30 miles west of here, produces about 1.1 gigawatts of electricity, which is 0.1% of our total, but locally it has certainly a big impact. For those of you who aren't grid people, that's a map of the transmission grid. There are better visualizations to show, but this data is getting kind of sensitive, so we don't like putting up maps too often. A map that we can put up is the one shown in the lower right, which divides the grid up into, in North America, 4 large interconnects. We're part of the blue, which is the largest, which is the Eastern Interconnect. That whole blue region is essentially one electrical circuit. Then the other large interconnect in North America is green. That's the, not because it's more renewable, but that's just the color. It's, it covers the western part of of US and Canada, a little bit of Mexico. You guys in Texas are on your own with ERCOT. And then the Quebec is the French-speaking electricity. Okay, so what makes the grid unique? The grid is one big circuit. So when we operate this thing, we're operating an electrical circuit that covers a good chunk of the country. Disturbances can propagate through this circuit really fast. And I'm going to show you a simulation in a second of how disturbance can move through. Electricity pulses move at the speed of light, but the electromechanical disturbances move slower, but they still move at 1,000 miles a second. So what happens here in Illinois can easily impact the rest of the Eastern Interconnect within seconds, and that can cause a problem. Going along with this is we really don't have any mechanisms to efficiently store electric energy. Batteries work for small amounts, but there's not a lot of grid scale storage. The best storage we have is actually pumped hydro, which is where you take electricity and you run motors at night, you pump water up into a reservoir, and then during the day when the price of electricity is higher, you take that water and you run it through your generators and you make electricity. The economics of this are actually pretty good. You can get really high efficiency in doing that, but we're basically just moving water from one reservoir to another reservoir. And then the last part is that electrical circuit, people talk about us routing power through the system. We really don't route much power. We can indirectly control how power flows on the grid, but these electrons kind of have minds of their own and they just kind of go wherever they want to go. So it's a challenging system to operate, and we have to operate it on a number of different time scales. This is a chart from one of my colleagues, Pete Sauer, where it shows all the different time scales that you're dealing with in the electrical grid, and it can range from very short lightning propagations in the microseconds up to decades as you talk about planning. The one that I work in mostly is kind of the shorter time scale where we're balancing the grid sort of second by second and trying to keep things stable. Having controllable generation like natural gas is really helpful. As we add in more solar, it can be a really nice option, or wind, but it's less controllable because you only get it when the wind blows and the sun shines. And we have to make a grid that's resilient with respect to disturbances. When lightning hits the system, within less than a blink of an eye, we open up the line that was affected, take it out of service, you see the lights blink, and then the fault is cleared. A couple seconds later, we put the line in. But we have to be resilient with respect to ice. The image there shows some towers that fell in Quebec. That hurricane that came through on Friday night, it went 4 miles south of my house. And I was telling my students in class today, it actually went across one of our 345 kV transmission lines that goes south out of the Sydney substation, but luckily it didn't cause any damage. But sometimes they do cause significant damage. As David mentioned, cybersecurity is a big concern, so we're trying to operate a grid with a lot of things going on. One of the challenges we have is maintaining the frequency on the grid. And when you have a disturbance, such as a loss of generation, we need to balance the load in the generation. You lose a generator, the frequency starts to decline. If you have too large a disturbance, you can have major problems. What prevents the frequency from declining too fast is the inertia in the system. We have a lot of synchronous generators like you'd have on a coal plant or a nuclear plant that are spinning, so you have stored energy in the rotors on the machines. That helps to stabilize our system. Wind turbines, for the most part, we do not see that inertia. Solar doesn't have any inertia. So as we try to add more of this inertialess generation to the system, we're getting more and more challenges in doing that. And as engineers, we like challenges. The grid can fail dramatically. I had the opportunity to be involved in the August 14, 2003 blackout investigation. That cartoon there is my favorite cartoon from the blackout. I got that from George Gross, and it's true. When that blackout occurred, suddenly us power engineers became quite famous for a few days. Pete Sauer actually got to explain reactive power in the New York Times, so that's his claim to fame. Yeah, although the fame did fade pretty quick. Let me give you an example of how a disturbance can affect the grid. This is going to show a frequency visualization of the electrical, the speed of the grid, and I'm using a color contour where blue is going to be our normal 60 hertz. And as you go down to red and magenta, the color is going to indicate a drop in frequency. This is a simulation of a generator loss in the western system, and you'll see how it propagates through the system, hopefully. Okay, so it's running at 1/3 real time. There's the disturbance, and it actually goes like a wave through the system. And in the western system, the largest frequency excursion actually occurs in Alberta, even though the loss of the generator was in northern Arizona. What affects how deep the colors are, how low the frequency goes, is the inertia of the grid. So as power engineers, we're really concerned about the inertia in the system, and if you lose too much, there are actually protective relays that help to stabilize the system by dropping load. And one time, I think it was in 1994, there was an earthquake in the western system. I think it was a Northridge earthquake, and it actually split the system in half. So the northern part separated from the southern part. The northern part didn't have enough generation, so the under-frequency relays operated, and people as far north as Alberta had their lights go out for an earthquake in the California region. And we're operating one big electrical circuit. Okay, do I have a little bit of time, Alejandro? Yeah, okay. So let me show my movie of our part of the world. This is running in real time. It's the same sort of contour of a frequency disturbance, except now red's going to be low frequency. That's how a loss of a generator in northern Illinois would affect the frequency in the Eastern Interconnect. And it's fascinating how this stuff goes through and it kind of bounces off the edge and hopefully stabilizes. We're working on a project where we're looking at the impact of nuclear weapon explosions, high altitude nuclear weapon explosions, which produce something called electromagnetic pulse, an EMP, what their effect would be on the grid. Their effect is actually on the same order of time as this simulation. You get you get very fast, that'll fry electronics, but then on the order of seconds to a little bit longer than a minute, you get a pulse that affects the grid, causes induced DC currents in the grid, and that causes problems with our transformers. Okay. So what are some of the implications with renewable generation as we try to integrate in large amounts of generation? And keep in mind, right now, wind is only 7% in most areas, but in some places, wind is getting to be a significant part of the generation portfolio. I think Texas actually has achieved operations sometimes where they're 50%. Have you heard that? Yeah, I mean, it's in some moments, the ERCOT grid in Texas has been more than 50% wind powered. So we're getting there where we can power a lot of stuff with these newer, inertialess generation, but it is causing challenges. So it's, something we're looking into. I'm looking into it at the dynamics aspect. The issue you run into, and this shows how a frequency disturbance would occur in a low inertia grid versus a high inertia grid. The one that goes the lowest, 59.55 hertz, is a grid where you have slow responding generators without much inertia. One of the issues with a fuel source free generation, a PV where the sun is free, you try to operate that generator at its maximum output. If you have PV on your roof, you want to get as much out of it as you can. But that means there's no reserve associated with that generation. If you operate a wind turbine, you're trying to capture as much energy out of the wind as you can, and that's good, except there's no reserve associated with that generation. So if we lose other generation, somebody has to make up the difference, and if it's not this wind and solar PV, it's got to be the nuclear reactors or coal or natural gas. Dynamics are crucial in operating the grid. I like to show this image because it looks kind of complicated. This shows some of the grid dynamics that occurred in the last minute before the North America grid collapsed in August 14th, 2003. A lot of different dynamics going on, how it oscillates, and it oscillates with a whole bunch of different frequencies. All that depends on what devices you have connected, how much generation, how it responds. So it's fascinating and it's really kind of fun to work in. Control implications, us electrical engineers, we really like control. The idea with operating the grid is if you don't have control on the generation side, we're going to have to shift the control to the load side. The load has often not been seen as controllable, but there is actually a lot of the load that we can control, perhaps in benign ways, like you can set up devices, maybe your clothes dryer, so that if the frequency goes too low and you happen to be running your clothes dryer, it's got a chip inside of it that senses that, and then in a clothes-friendly sort of way, it decreases its electric load. So doing that can allow us to add more renewable devices and kind of mimic or help provide by the inertia lost by the generators. And the famous New York Times person just walked in. I showed the cartoon where it made power engineers famous after the August 14th, 2003 blackout, Pete, and I said, you explained reactive power to the New York Times.
Yeah, that was fun.
Yeah, those were the days. What?
A physics professor in New York called me and asked me if I was joking. The title of the article was Imaginary Power.
Oh, yeah. Some of the research that we're working on right now is trying to figure out how we value the inertia provided by devices like large nuclear power plants. If you take a plant like Clinton and you get rid of it, you've lost something, you've lost inertia on the grid. Should that inertia be valued? And then something that we're looking at is, does the location of the inertia matter? And what we're finding is, yeah, if you take out too much inertia in regions of the grid, so if you were to take, maybe Illinois and totally get rid of our base load generation, we went totally wind and solar, it might have implications. And I will say the last thing is, one of the drivers of this research is we need access to synthetic models, and this is actually my coupling in with iSEE, is we're doing a joint project where we're looking at coupled infrastructures, the electric grid, and my students working on coupling in with the water infrastructure. One of the challenges in doing this is grid models of the actual grid are confidential, so it's hard to publish results with them. So we're making fake models, what we call synthetic models, that mimic the complexity of the actual grid, but don't disclose anything confidential. So if I show you the transmission grid of Illinois and you look at this, it has nothing in similar except it's very similar in structure. The good thing then is that we can couple these synthetic models, which have the actual generators in them, with stream flow models that Ashlyn is, kind enough to provide me, or our students, I guess is better to say. And it's a good way to do research on coupled infrastructures. So I guess we're going to do questions at the end, and I'll turn it over to Miroslav. I guess you could do this, but.
Sure. Thank you. It's a pleasure to be here. Believe it or not, this is my first time in Urbana-Champaign, even though I've been in this country for 32 years. So I'm glad that I'm having that off my bucket list. Topic of my conversation or presentation today will be integrating solar PV with the grid, but more from the PV side. I will tell you something that many of you probably know, but oftentimes I discover that people are unaware. Albert Einstein did not get his Nobel Prize for neither general nor special theory of relativity. He got it for explanation of photoelectric effect. And that's how we got where we are with solar. Second thing I want to start with is that all this talk about sustainability and renewables should be taken with a grain of salt. There's only about 5 billion years that we have using the energy of our friendly star, and that's not sustainable in my book. So we've got ways to go to discover other things, and I've been reading about these planets around nearby stars, but definitely all energy that we're getting is coming from the sun, and that is limited, time limited, hopefully much longer than we'll need. So solar has been touted a lot and has been used for several decades, and for a good chunk of that time it was very marginal, and it was used in space to a great deal, but much less so in grid. And that has started to change in the last decade, I would say, maybe last 20 years. One of the International Energy Agency reports from 2014 predicts the solar power domination by 2050, but even then they say PV could generate as much as 16% of the world's electricity. And then solar thermal could be added for another 11. And then, concentrated solar power could help with cutting the emissions, and all of that conditioned upon price decrease of about 50 to 65% by mid-century. So that's rather significant. What's the big problem about solar cost? It's been used for a while, and the cost remains relatively high. We'll get back to that in a moment. This is more recent news. This is September 8th, 2016. As a former president of IEEE Power and Energy Society, I'm not happy to say that it's UL laboratories that have published a new inverter standard, because the one that IEEE is working on, we thought would never be finished, and now that it is finished, it's attempted to be changed, but it's still imposing certain restrictions on the distributed generation that are very inconvenient. One of them is required islanding in case of disturbances. So this new inverter standard called UL 1741 Supplement A is enabling the testing and certification of inverters for distributed generation, test methods, and the ability to stay online to stabilize the grid during disturbances. So this is the first time that such a standard is actually being accepted and implemented, and California is merging it with its own Rule 21 grid interconnection requirement, which is used as a source requirement document for implementation of solar. That will help to some extent things that Tom has talked about, because inverters can do a lot more than just provide power that's generated by the panels. It could create a virtual source of inertial energy that can mimic rotating machines and help with spreading and controlling of the frequency disturbances. It can provide reactive or imaginary power that Pete has talked about in New York Times. All of those functions are quite important in maintaining the grid operating safely and reliably during times when disturbances occur. On the other hand, one of the problems with solar are clouds. Solar, as we know, is not as reliable, and wind is notoriously unreliable, because we don't really know how much solar there will be, depending on the passing clouds, depending on the weather moodiness. There may be plenty of energy, or there may be little energy, and when there is no solar, there has to be something else. And that something else is either storage or an alternative source of energy. And if we have to build gas turbine for every solar plant that is there, then there's little benefit from it. So US energy storage market is rapidly growing, and 41.2 megawatt of energy storage was deployed in second quarter of 2016. Put that in perspective of what Tom said about Clinton plant, which is 1.1 gigawatt, and you'll get a picture of how little that is. And that is being touted as an increase of 126% over the first quarter of the year. So the good thing is that this deployment is happening in Midwest ISO territory rather than in places where it's traditionally being used, which is California ISO and PJM markets. So the White House is providing a boost for installation of about 1.3 gigawatt of new storage capacity, and that may start changing things a little. But the storage is needed, and current storage, as was pointed out earlier, is primarily based on pumped hydro. So let's stop talking about solar for a moment and look at some of the energy-related issues. In Europe, large cities produce about 80% of gross national product, contain 68% of the population, and is expected that to grow to 85% by mid-century, consume 70% of the energy, and generate 3/4 fully of the greenhouse gas emissions. In US, it's not just the cities, it's where the cities are. So the average home in Pacific region is consuming 35% less than homes in the region where I live, South Central. And New York has the lowest per capita energy use, partly because of the urban and smaller apartment style of living. Wyoming has the highest, 500% higher than New York, or 1 billion BTUs per year. So it's very diversified as far as magnitude of consumption. Resources are being consumed in a way that is taking up huge amount of energy. The top 7 materials used in industry, used for all kinds of things like concrete, like steel and asphalt and so forth, they are requiring on a continuous basis, 24/7, 10% of global power and energy generating capacities to be used, 1.5 terawatt. So that's a huge amount of power that's going into that. Looking into water resources, if we took all of our surface and underground waters on the planet and put it all in one little sphere that you see on this slide, that sphere would be about 800 miles large. So that's all water that we have. It's very misleading when we look at the globe and see Pacific Ocean and Atlantic Ocean. They're only very thin, and water is not nearly as plentiful as we think it is. So water resources and impact of using water in generating energy and doing industrial activity is also quite important. Then generation technologies of electricity. For decades, it was thought, and in the Ole Elgert's book that I learned my basic power engineering from, it is mentioned as a certainty that by the end of the 20th century, the bulk of electric energy generated in the world will be coming from nuclear power plants. Well, what happened later, we all know. 3 Mile Island, and then several other disturbances, and Fukushima, Chernobyl, Fukushima, all of that, during which time we've seen prices of nuclear go as little as $10 to $20 per megawatt hour. But after Fukushima and after all the decisions, somewhat rushed decisions by some governments to shut down all nuclear capacities that they have, like German government's decision to shut it all down by 2022, the attention was being to be paid about security and resilience of nuclear energy, and that has raised the estimated cost of nuclear to over 100 euros per megawatt hour. Now, when you compare that with Fraunhofer's estimate of German cost of solar of about 80 euros per megawatt hour based on location, based on technologies that are currently used, that's not that large of a difference. So how does solar function? Black body radiation shows roughly the outermost, the orange part of the spectrum, which is generated by sun. By the time it passes through the atmosphere, it generates the blue portion with much of it being absorbed. And then because of the limitations of the technologies that we are using, which depend on the band gap of the materials, and predominant one is a silicon, we have the green fraction of that spectrum, which is the only part of the energy that is actually possible to be extracted, unless we use multi-junction cells and very esoteric designs that can extract more, but at exorbitantly higher price. So that's not much of an option. But that's why when you read about solar cells, you typically see efficiencies of 15, 20, 25% is the world record. Theoretical limits are of the order of 30% or so. So that's the limitation. Unless we discover a more friendly technology for extraction of energy, those limitations have to be dealt with. Now, the cost, producing solar cell, which is a thin layer of silicon that is designed basically as a diode, which absorbs the energy of photons and tries to convert that into electric current before the electrons that have been kicked into conduction zone get recombined back into that crystalline structure. That process is very expensive. It is estimated that with modern technologies, it takes about 18 to 24 months for solar cell to generate the energy that has been invested into its production. Current prices, which were 20 years ago about 4 times larger than they are today and more, are going down to the level of about half a dollar per watt of the installed capacity. And you see how in the process of generating polysilicon wafer and constructing cell out of it and creating a module by assembling multiple cells, the small amounts of cost get added, and there's not much that can be done to reduce this substantially below this level. Stephen Chu has said a few years ago that his belief is and hope that we will see at some point $1 per watt for installed system, and this is only half of the story. We have something that's called balance of system, which includes all of the rest, not just the modules, that needs to be in place for a solar plant to function well. So what impacts the effectiveness of a cell and cost of electricity that it can produce? When you look at module efficiency on the vertical axis here and the cost of the module in dollars per watt, these differently colored bands represent the ranges of costs per kilowatt hour that such cells are possible to generate. So it's important to generate very efficient cells at very low cost. And the red dot represents the aspirational target for most manufacturers who are using mono or polycrystal silicon to get around 20% efficiency at a cost which is $0.6 or $0.5 per watt. And if that's accomplished, then we are looking into the cost levels of 10 to 20 cents per kilowatt hour based on, of course, favorable location, based on 25-year lifetime, 20% derating factor, and all of the things in the fine print that you can see in the bottom of this slide. On the other hand, cost of the cells is not only fraction of the technology that is being used, but also the volume of production. That's the economies of scale. And this graph represents how, since 1976, that cost has been steadily going down as the cumulative capacity in gigawatt has been going up. So we're seeing fairly good and predictable estimates that are in this graph projected up till 2035, and that level is about $0.50 per watt. When we look at the implementation, the levelized cost of electricity and grid parity is what we're after. Electricity costs different amounts in different places, and electricity has different resources in different places. Arizona is very different from Quebec. So when we compare those things and look at these boundaries of levelized cost of electricity in 2012 and 2015, we are seeing how the moving of this boundary due to a lower production cost in different locations is including more and more of the locations into the realm of what can be considered a cost-effective production of solar energy. So this is an interesting way to look at the picture, because places like New Jersey are still borderline. South China, with its low cost of electricity and building one coal plant every week, will probably not anytime soon be a candidate for levelized cost, even though it's one of the biggest world manufacturers of solar energy. So when we look at global capacity additions, the blue band represents the inclusion of new solar and estimation through 2020. Wind capacity is shown as the darker band on top of it. We see that substantial portion of it now is becoming solar and wind. That was not the case in the past. And when we look at comparative costs of energy production, this is from the standpoint of cents per kilowatt hour. Solar is here represented on top of the picture with utility scale solar, commercial solar, and residential solar, which is outlined because it's by far most predominant at the moment. So it's 7 to 25 cents a kilowatt hour. Why not utility solar? Utilities are at the moment not interested in solar because there are cheaper ways of doing it. Solar is not yet attractive enough to them to use it, and rightly so. There are many other ways to do it. How does it impact sustainability is another story, but there is little economic incentive for utilities to go large scale into solar. That is estimated to change by 2030s or so, where there may be both policy and regulatory incentives to consider wider implementation, and utilities may change their mind about it. Looking at evolution of electricity prices, We are seeing in the last decade about 20% increase of electricity, and superimposed on the very volatile and moody behavior of gas prices, it seems like electricity pretty persistently is going up. It doesn't matter whether gas is cheap or expensive. Electricity prices have only one way, and that's upward. So that's making it easier for solar to become competitive. Famous duck curve. I know few people who didn't show it in their presentations on solar energy. It is simply showing one of the problems that occurs when we use a lot of solar electricity. The topmost curve, showing 2012, which is not actual, but it was 4 years ago, shows the typical load curve in California on a typical day. And as years go by and additional capacities of solar that are estimated to be installed in California take place, the production of solar will effectively change the load to become a lot more depressed and smaller in the midday, but not when it's most needed, which is the peak time in the evening hours. So we're getting a substantial reduction and then a rate of change of the load curve that is far larger than what would it be if solar were not used. So we have to have alternate resources that will cover that huge peak. So solar cannot do it unless there's something else to shift the use of energy. And that something is storage. So if we take the same curve or similar curve and try to use the lower period of the load to store PV peak in the battery or in pumped hydro, which is what we see in the left peak, then we can release it in the right peak and obtain what is shown in the dashed line, where the load curve is essentially flattening midday and remaining flat up until peak passes on. So this is the impact of storage if it were available at large enough capacity. There are multiple storage technologies that I'm listing here. They are mechanical, like pumped hydro, which we have talked about. There are more esoteric and smaller, like flywheel and compressed air, and electrochemical, like batteries, suitable for transportation, but there's really no capacity scaling that is enabling electrochemical storage to become a substitute for pumped storage, for example. And then we have electric with ultracapacitors or magnetic, supermagnetic coils, and then thermal storage with molten salts, which can transfer the use of thermal cycle into evening hours to cover the peak production. So all of those are being explored, and experimental test beds are being built, but no storage technologies at the moment are large enough to accommodate a penetration of solar that would be on a scale of those that have been predicted by International Energy Agency in their report of 2014. So California is now, as I mentioned, doing a little bit of an incentive to produce 1.3 gigawatt by 2020 and experiment with impacts of that. That is a good and interesting incentive, but we'll see how it all works out and whether there will be a revolution in storage that will enable a larger procurement of those devices. Currently, largest solar plants in the world are still in the hundreds of megawatts, ranging from about half a gigawatt on top of the list to about 150 megawatt in the bottom of the list of top 10. So the plants are much smaller. We are talking utility scale plants. Residential, of course, are of the order of a few kilowatts, and they are truly at the level of household consumption. And that is a severe limitation of projecting their use far into the future because of all of the problems with uncertainty and volatility of output. So what are the takeaways from this whole brief overview of solar? It is growing fast. I didn't even tell you about the problems with production, Chinese overproduction and undercutting of the prices, US retaliation with taxes, problems with US companies going bankrupt, trying to cope with it all. In spite of it all, there is a 25% growth in 2016. There is distributed PV in China, but not nearly to the expectation that is commensurate with their capacity to produce it. The storage installations are growing rapidly, but on an infinitesimally small scale, so that remains, gives us a long time before we see any of that sufficiently widespread and of sufficient capacity to operate well. And then we have many of the emerging markets showing promise for substantial installations of solar. Monocrystalline technology, which was dominating solar for years, is still doing so. It's not 2015, it's 2016. And systems up to 100 kilowatts account for fully 1/3 of global installations. That is the depressing thing because of the pricing components and ramifications that we talked about. California in the US is becoming leader, not only nationally but internationally, in solar power penetration. And that's the end of the story at the moment. I just want to take you back for a second, 20 years ago, to Georgia Tech, where I worked at a time, and where we built a 340 kilowatt system on the roof of the aquatic center, which was to be used then for the Olympic Games, in the hope that the helicopters showing the Olympic site will show a little bit of a solar, which was ready for a major breakthrough. Well, it took 20 years to see a major breakthrough, but I'm happy to say that system is still on, still functioning, producing about 400 megawatt hours a year, and it's been a great toy for us to play with and learn from in the past 2 decades. So it was a good investment in spite of what was then a huge price of $5 million to get it done. Thank you very much.
There's a microphone.
Yeah, we've seen this duck curve now several times at this meeting. So what about facing a whole bunch of solar photovoltaics west? So I actually own some photovoltaics on my house, and I do have some west-facing ones, and they produce less electricity over the course of the year by about 20%, but they would all help with that duck curve.
That is true, but 20% means you have a cost not of 10 but of 12 or more cents per kilowatt hour. We've done studies on that in the 90s, and at that time the cost was so exorbitant that it was not even reasonable to consider that. Even with that, you cannot expect to compensate the peak at 9 p.m. with a westward facing solar. So there's only so much that can be done, but I don't think that we have a way of compensating for the time of the day use. We either need storage capacity, or we need a spinning reserve of some other resource that is not time dependent, or we need a demand response which is very responsive to these needs, or a combination of all three.
One issue that grid operators have talked to me about, so folks at independent system operators, is that the way solar panels are set up right now, if the frequency on the grid starts getting slightly outside of a certain range, they'll just start tripping. And since often the operators don't know exactly who has solar, like the utilities do, but the grid operators don't, they sometimes find, oh, look, now we're even farther out and we have to do more things to try and get back on. Again, I'm probably butchering this because I'm not an electrical engineer. But this concern they've had, and they suggest new standards for inverters or something are needed to try and link either the inverters with the grid or somehow link the solar panels better with the grid in order to try and alleviate this potential concern of them all tripping at the same time, thus leading to additional instability on the grid. And I was wondering if you know anything about this issue or have thought about it, or is this not an issue at all?
Could you tell me again the disturbance that that you are concerned about? I'm not sure I understood.
Sure. The concern is that when say a power line goes down somewhere and it's starting to ripple through the grid, when that happens, the solar panels will also drop off, so that their generation drops off the grid, which exacerbates the issue that they already have already in trying to keep the frequency within the range. And so there's discussion about trying to develop standards that will have, if if the inverter shouldn't go off, because they know that if it stays on, they will be okay. But when they all drop off, then they're going to have more trouble.
Well, the problem is that solar plant cannot produce more or less power than what its input is at the moment. So it can stay on during a disturbance that disconnects the large portion of the network, only if its load is perfectly matched with production. So that means there should be a clever system that keeps just enough load connected to the solar plant and isolates it from the rest of the system, or it would go down. That is not easy, because there is no frequency sensitivity or other inertial framework that would help estimate the balance between the load and production. On the other hand, it is possible nowadays to do that, but the current regulations do not allow it because of the safety concerns when things happen that require maintenance or repair on the solar plants. It is necessary for personnel to approach. They cannot work on the solar plant that is producing energy, and for that reason, the islanding operation was discouraged in the previous versions of the standards. So it is all about to change, but it is about to change because more modern inverters are being designed which can handle more of these problems, including assessment of the balance between load and generation in a dynamic fashion. And as that is happening, we'll see more and more of that actually being used. But for decades, the problem was you don't know how much load is there. If you connect, there's so much load, it shuts down immediately, so there's no point.
And let me give a public service safety announcement. When your house blacks out, okay, your house may still be connected to the distribution system, and if you take a generation source of any type and use it to energize your household wires, you can backfeed the distribution transformer and put a high voltage on that transformer and end up killing people because of that. So if you have a device like I have one in my house, a backup generator, that has to have a transfer switch on it. That switch senses when the grid has gone, disconnects my house from the grid, then my generator can start up and I'm fine. So when you have distributed energy sources like solar or whatever at your house, they have to drop out if your house no longer has a grid voltage being provided to it. And as part of these standards is safety.
So apologies for monopolizing the microphone at this table. Okay. Professor Begovic, could I ask you to go back to your experience curve slide, please? I have a question about that. The one that shows declining costs with cumulative investment, economies of scale. Yeah, there we go. Mm-hmm. So maybe this is a little pedantic, but I actually think it matters. There's two things going on, if I understand correctly, in this graph. One is that material science and other disciplines were improving the way that a PV cell would work, which is not a scale economy phenomenon. It's simply an improvement in any one cell. The other is some scale economies, which I think were being realized only a lot more recently when you had major expansions. So I'm uncomfortable with the idea of having one trend line like this that then gets pushed out all the way to 2035, because I just don't think that's a reliable projection. I think you have to separate out the cost reductions that came from improving the PV performance itself with modern films and all the rest, versus what happens when you take an established sort of technology and simply make it work a little better by scaling up. I'm not sure that we can say that things will be that much cheaper in 2035 than they are in 2015.
Well, there are already experiments which are demonstrating that we are not far from the estimation on 2035. But one should remember that predictions are always unreliable, especially about the future. So it's not easy to know what's going to happen. If we look at this more carefully, I didn't have time to show that. But if you see, there is a small portion of the curve which is horizontal right around the 5 gigawatt production level. And that is the period of time in the early 2000s where the interest in solar was growing primarily due to European governments' support and subsidies without any major improvements in technologies. And then an abrupt decline below the regression curve, which is due to the economic collapse of 2008 that has caught unprepared a bunch of manufacturers in China, US, and elsewhere in the world, so that they have sold their stock way below the prices they were hoping to sell it for. So what we are seeing is a recovery curve in 2013 to 2015, which is taking a little bit of a constant pricing as the quantity is increasing. And there are small improvements in the technologies of monocrystalline silicon. One of my colleagues at Georgia Tech actually started a company and is producing close to 200 megawatts of capacity. So I have discussed this with him. There are small improvements which are not very costly that can show slight increase in efficiency, which is equivalent to lowering the price. That is making him confident that further price decrease or price versus efficiency decreases are possible. This is not to say that the regression curve works wonderfully well, and especially not at high volumes like this. Most of the potential for exploitation of these is happening in the low capacity part of the curve. What will happen at this end is just streamlining the manufacturing process to reduce any inefficiencies in energy use, any high cost issues in collecting and manipulating toxic substances, of which there are many in the production process, and that is what contributes mostly to this part of the curve. There is also unexploited potential of using reduction of the cost in balance of system, and that is something that leaves a lot less high technologies to be used. That is simply how do we produce tracking or stand devices which are cheaper and equally robust? How do we produce cheaper wiring and everything else? Inverters. Inverters are notoriously bad because their lifetime is about half of the lifetime of the modules. So if we can design an inverter that can last 30 years just like modules, well, a substantial portion of the cost would be reduced. But that's not included in this graph. That's the graph of the completed system. So there is potential for cost reduction. It is not exuberantly optimistic, but it's not zero either.
I think there was a brief mention or a bullet on emerging markets and worldwide emerging markets for solar, but I was wondering also a little bit more about that, but also areas of the world that experience brownouts or rolling brownouts or blackouts. Are there things that our grid can learn from those areas as well?
Your question was, can we learn from areas of the grid that experience rolling blackouts? Is that what it is? One of my concerns with the grid is, I like reliable electricity, and as a modern society, we're very dependent on reliable electricity, getting more and more so. So when the lights go out, none of us know what to do anymore. And, we don't even know how to navigate our cars anymore because people are using, the GPS system. So if you talk about large-scale blackouts for this country, such as, David's cyber guys might cause, or the people he's trying to defend against, or when I was talking about the large-scale events like an electromagnetic pulse attack on the grid, that could be very concerning. Also here in central Illinois, we had tornadoes on Friday, and they were relatively small, a tornado, I guess. In parts of the South, they've had major tornado outbreaks that have taken the grid down for days and weeks. Here in Illinois, we could get a major ice storm that could leave us without power for 2 weeks. So I think as citizens, we should be prepared for that and do what we can to, be able to ride through it, whether it's having a backup generator like I have or having food on hand, things like that. So I think we could learn to be a little bit less reliable on the grid or dependent on the grid, not because we don't want it there. It's great, but it may not be there all the time.
Okay. One major issue in sustainability is what happened with solar energy in developing countries. I spoke with some manufacturers, and they said that they build solar in the US because of the subsidy. They build solar in other parts of the world, especially in Africa, because they make money. So, because the opportunity is diesel or other sources. So what do you think about the potential of solar in developing countries that don't have a lot of the alternatives that we have here? And what about challenges of designing the grid in the third world?
Well, it was mentioned in the previous session that part of early solar applications in underdeveloped markets is simply to produce the very basic supply for lighting, for charging the batteries on the phones, things like that provide very basic quality of life, but not to provide heating or cooling. We have huge parts of the world which are not electrified at all. Sub-Saharan Africa has 630 million people that have never been connected to the grid. And that is supposed to grow by 2030 in spite of the electrification efforts. A speaker from World Bank could probably tell us more about effort that I've read about, which is substantial collaboration with many governments in Southeast Asia on, I think, investing $27 or so billion trying to provide basic electrification and change the use of cooking oils that was unhealthy for population. So looking into solar is for energy supply, similarly modern technology as smartphones and wireless phones were to the communications. It provides opportunities at certain level, but the energy needs are far higher and larger than what solar alone can provide, and will not be met by growing solar alone, particularly because of the compounded issues of storage cost and lack of advanced technologies to manage load and generation concurrently that will be needed to see microgrids completely independent of the grid. So there is great potential for providing very basic services, but there is a long way till those needs are met at a more substantial level. I don't know if I answered your question, but I attempted at least.
Question here. You want to ask something?
So like Thomas, was it? I think, yeah, he touched upon like a big point that we are very reliable on our energy. And I feel like that in a sense really is energy security. And so I was wondering with, because we had brought up the idea of microgrids earlier, like would those be more secure than our current grid? And like, I guess generally how in the cyber world, how secure is our grid currently?
I'll give that how secure is our grid currently to my colleague here to address.
Well, I like to quip a couple of things. One is that I think the main reason why the lights are on is because the Chinese think we're going to pay them back. The point being, we are certainly susceptible to acts of war by nation states. The concern, the greater concern perhaps, is for entities that aren't so concerned about going head-to-head with the United States in a war, and those would be fringe groups. So what am I saying? I'm saying that the grid is it's an amazing machine. And as Tom points out, and these interconnects they're one great big circuit, and they are very, very well engineered. They're very, very well engineered to protect against the disturbances that can be anticipated, and those would be natural disturbances. But where things get interesting with cyber is that it's possible now to imagine disturbances that haven't been imagined, that might cause this very complex machine that's ruthlessly following the laws of physics to do interesting, damaging things if it were coaxed in certain ways by certain kinds of inputs. So good news is lights haven't gone out yet, and so that's a good thing. I'm not going to be surprised when they do. I hope that it's not going to be widespread, but I do think it's just a matter of time in this country before there is some chunk of the grid that goes down for a while as a result of combined physical and cyber attack. The real question is how big a chunk and how fast can it come back?
And let me make a quick comment on your issue about microgrids. I think all of us here are big fans of microgrids. They're an interesting research area. They're growing in popularity. So they're good, okay? And backup systems are good. Like I have at my house, we hope that our hospitals, our water treatment plants have backup systems that can last for a while. But any of those systems, to create a microgrid, you have to have enough generation there to meet your needs, and you have to have enough fuel source to continue running. That's great if you've got solar and wind and enough storage capacity to ride through a disturbance. But a lot of times you don't have that in a microgrid. A lot of the microgrids, and the military's pushing microgrids because they want to run their bases for a long time if the regular grid is down, and they have the money to install solar and to install natural gas and have the storage capabilities to run without the grid. And could University of Illinois run as a microgrid? Well, we've got Keith right here. He could tell us. And to do that, we'd have to have enough generation capacity, and we'd have to have enough fuel to keep our grid going for a while.
Well, it is to be expected that standalone microgrids will provide some sense of security, but we shouldn't be fooled that security will be complete. Tom mentioned that certain disturbances may disconnect microgrids from the grid for a couple of weeks, and it depends on, or longer. So it depends on what is the autonomy. If it is a tank of diesel, that's the autonomy of how long we can count on that. If it's something else, it's the same thing. So I think there is a long way before we see the reliability of microgrid substituting for the security that the grid is providing for all the customers.
Well, that was a great last question and discussion follow-up. So with this, we are going to close this session, and I would like to thank the speakers again. Thank you very much.